Thank you, Mitch. Good evening, everyone. So appreciate you guys joining, and we have a very exciting night for you involving DX split systems. We're going to dive into some of the design and application much further beyond just a selection out of a catalog. I'm Randy Stevens, engineering manager out of the Trane Chicago office. I have Mike Petri, who's our senior applications engineer. The idea on this forum is that we really encourage discussions, especially during and maybe after a few slides. We might pause for a while and feel free to open up to discussions. We like to have engagement because it's difficult in this format, as we're all aware now with the virtual. So any engagement's welcome. The Q&A function, as Mitch described, he will help us moderate that. So feel free to type your questions throughout. We'll stop and answers periodically, about 3 times throughout the presentation. So with that, hand it over to Mike to get us started.
Randy, as I said, I'm Mike Petri. I've been in the Chicago area here for 50 years, representing Trane and other manufacturers over the years. Randy and I work with our sales engineers and our customers to provide application support, and we see a lot of split systems. I'm going to turn my camera off here so that we don't have any sound issues. But okay, so this is what I think we're all pretty much familiar with the way split systems look. We probably have one in our homes that looks a lot like this, where there's a condensing unit sitting outside that has a compressor and a condenser in it. Inside, we've got an air handling unit that's got an evaporator coil, and there's tubing that connects the 2 pieces together. Most of these systems use a simple wall thermostat to control the compressor. It just cycles the compressor off and on to maintain the space temperature. And that's usually adequate for a house. And then when it gets to be 70 degrees, a day like today, I doubt that many people are actually using their split systems, but the window there in the picture probably gets opened up and takes care of the cooling needs on mild days. So it's therefore a pretty simple and inexpensive way to cool a home. So you can use these in commercial projects as well. And the next slide here shows a medical office building. Randy, want to advance the slide? There you go. This is a medical office building that's got 3 split systems. The one on the left is actually a 200-ton air handler with 2 100-ton condensing units. On the right, we have another 2 systems. There's an 80-ton and a 120-ton system over there. So these are much more complicated than the first slide, that they have ventilation requirements. These units serve tenants and procedure rooms in this building, and they have much more complicated control systems than the first slide. They're variable volume systems, so they need to work over a wide range of conditions. And you can see the piping visible there on the left-hand system. It's pretty complicated refrigeration piping. Randy?
Thank you, Mike. So as Mike described earlier, the discussion topic that we're going to focus on here is really around large commercial applications, which most of us work in that industry. But despite the difference in size and complexity, the same basic refrigeration cycle applies. So I'm going to start from scratch here. So for some of the younger people that may join us, let's start at the discussion on the basic refrigeration cycle and components. And maybe even for a number of us experienced people who just forget how this stuff works after a while. It's normal. But if we go and start here at our evaporator, the basic refrigeration cycle that's most commonly used in air conditioning applications consists of 4 main components here. We have the evaporator, compressor, condenser, expansion device, and bunch of different things in between, including controls, but we'll discuss the operation of these real quick from the basics. The evaporator is most often a coil, fin and tube style, that is paired with an air handler, some air moving unit or device, and it extracts heat from the space that's trying to be conditioned, and it absorbs it and evaporates the refrigerant that is inside of the system. So nowadays we're using R410A. We used to use R22. We'll discuss a little bit of that later, but the heat that is absorbed evaporates the refrigerant within the coil and moves over to the suction line. The suction line is in its gaseous form, superheated vapor to make sure it's a gas as it enters your compressor. And then the compressor compresses the gas, big surprise, to a higher pressure into the discharge line. The discharge line then moves this high pressure, still gaseous form refrigerant into the condenser. Condenser coil utilizes an ambient air heat sink to then reject the heat from this conditions or the space we're trying to condition to the outdoor air, which is at a lower temperature than the refrigerant at that point. And it condenses into a liquid form, subcooled liquid to ensure, again, it's liquid form, back to our thermal expansion device, which at that point strictly reduces the pressure and flashes off into mixed vapor, some liquid, some gas, back into the evaporator to restart the cycle. So in our systems that we're talking about today, in the split systems, most commonly the compressor and the condenser are combined into a single packaged unit, known as the condensing unit most often, or air-cooled condensing unit. And they are connected by field piping, whether it's a short length or really long length of liquid line and suction lines, to an indoor, most often indoor unit or outdoor air handler style that contains the evaporator expansion device. So as we go through this slide, the slide deck here in the details, our biggest components that we're focusing on here are right here in our suction line. We want to ensure that that is sized properly, and in hopes of making sure the oil that's inherent in a refrigeration system, which is used to lubricate the compressor, makes its way through the system and back to the compressor where it's needed the most. So it's a critical spot here in the suction line. And then elsewhere, as we have a focus on oil, energy efficiency, and minimizing the refrigerant volume of the entire system itself, those are our main goals as we focus going forward. So I will turn it back over to Mike to talk about some industry knowledge. Real quick, is there any questions from the basics? All right, go ahead, Mike.
So when I started back in 1970, R22 had just become the most common refrigerant, replacing R12 in HVAC projects. And at the time, it was the new high pressure refrigerant. Boy, there was just as much concern then as there was just recently when we changed R410. But the picture in the photograph here shows a compressor. This is probably about a 60-ton reciprocating compressor in this photograph. And a typical system back in those days would have a compressor like this mounted on the floor next to an air handler, maybe a water-cooled condenser with it. And the electrician would hang a starter on the wall for this thing, and you can see the power terminals in the foreground there. The control contractor would hook all this stuff together, and then we'd have a system. Remember, at the time, Kmart was building hundreds of stores around the country, and this was a very common system. They might have two 100-ton compressors like this sitting on the floor, and a big coil bank with a big fan blowing air around the store. And today's big box stores just use a bunch of small rooftop units, but this was a pretty common occurrence back in the 70s, that a lot of these big systems were popular, and the pipe fitters knew how to install them. I remember my father was a pipe fitter, and he carried a refrigeration manual around in his lunchbox that would answer questions for him as far as how the pipes were supposed to be all hooked together. And like Randy said, you knew that the suction line needed 1,000 feet per minute face velocity up the pipe to get the oil back to the compressor. And it was just all the manufacturers followed the same rules back then. These compressors had unloading capabilities so that the volume of refrigerant that they pumped would change with the load. And so some of the pipes required double suction risers to make sure the oil could travel uphill to the compressor again. Do you want to advance the slide, Randy? So today's compressors, we're using more scroll compressors today due to efficiency. So the new systems have manifolded scroll compressors. They use R410A for the past 10 years. And recently, microchannel condenser coils have taken over because of the reduced volume of refrigerant that they use. So this has made a lot of changes in some of the rules that we followed with R22. The pressures are higher, the refrigerant volume is less. Oil and refrigeration management is much more critical than it used to be. So it's evolved into new piping practices, and each manufacturer seems to have their own rules. The manufacturer usually has a warranty involved that sometimes is a 5-year compressor warranty. So we're very concerned about the way the installation is done, and it is important that you follow the rules of the manufacturer that you're dealing with. So you advance the slide, Randy. So how do we cope with all these changes and still end up with a successful project? So in condensing unit catalogs, you'll find curves that look like the chart on the left here. What this shows is tons is on the vertical axis and saturated suction temperature is on the horizontal axis. The blue lines represent, and this is probably a nominal 20-ton condensing unit that is operating at various ambient conditions. So 95 is the accepted design ambient in Chicago, so we'll concentrate on this. And what this shows is that in this example, at 45-degree suction, this combination will give you 20 tons of refrigeration capacity. What it shows is as the evaporator, as the ambient temperature increases, the capacity falls. That's because the compressor now has to lift the refrigerant to a higher state to get it above the ambient temperature to reject the heat of the condenser. Also shows that as the suction temperature falls, capacity is again reduced because, again, the compressor has to do more work to lift it from a colder state to the higher state. Now on the right, you see the evaporator coil, and the opposite is true there. As the refrigerant temperature falls, the difference between the saturated suction temperature and the airstream increases, and therefore the thermal heat transfer of the refrigerant increases. The capacity of the coil is greater with colder suction temperatures. So it's important that these two pieces fit together, not like our nut and the bolt at the bottom of the screen. We want these pieces to be matched so that they work together. So you can advance the screen. Also, the two pieces might not be made by the same manufacturer. We might have a condensing unit from brand A and a coil from brand B. We see this a lot.
Yeah, just to follow up too, as we noted here too, the most often way we see it designed, and kind of the status quo, is to schedule your condensing unit separately and your evaporator and your air handler and your coil separately, independently at ASHRAE full load design conditions. Go ahead, Mike.
So in this example then, we have a balance point calculation showing how we take the evaporator curve and superimpose it onto the condensing unit curve. And the way you do this is you run the evaporator at two different operating points. They may be 40-degree suction and 50-degree suction. Draw a line between those 2 points on the chart. Now, the one important thing though is that in order for there to be flow from the evaporator outlet to the condenser inlet, there needs to be a pressure drop to force the gas from the evaporator to the compressor. So the normally accepted range for that is like 5 psi. And then with R410, that's about 2 degrees Fahrenheit. So what this chart is showing you is that the balance point is really two different points on the curve, that the evaporator is 2 degrees warmer than the actual condensing unit. So to schedule this equipment properly, the condensing unit schedule should show 20 tons at 45 degrees suction, and the air handler should show 20 tons at 47 degrees suction. If you do this, then it doesn't matter whose condensing unit or whose evaporator you're getting, as long as they meet those capacity constraints, the two should work together. So you want to advance, Randy?
Go to the next slide. Do we have any questions, Mitch, or are we good to go?
We are still good to go. Again, everyone that's joined us, feel free to use either the question and answer feature or the chat. We can see both here, so I'll be happy to call out the questions as they appear. Otherwise, you can raise your hand as well. Looks like John is looking to raise his hand. Try and figure out how to do that. His hand raised, and then it looks like he went back down. And we'll let him ask his question via Q&A or chat, and I'll be sure to read it off.
All right. And we have one from Pat.
Okay, so point number 1 is the balance point we just discussed, where the two curves cross. And what the right-hand curve is showing you is that in a constant volume system, as we said earlier, the common in a constant volume system, when we turn compressors off, this example would show you a 20-ton unit with 4 5-ton compressors in it. So at point 2, we've turned off one compressor, and the suction pressure has gone up a little bit because the capacity has gone down a little bit. So what we see is when we get way over to number 4 with just one compressor running, the suction temperature is raised quite a bit, and the leaving air temperature will have risen with it because we're at less capacity. What this means is that we're not going to have as much dehumidification as the design point. So the left-hand curve is showing a variable volume system, and the point 1A here is now fallen because with 50% airflow, the coil will have much less capacity, not necessarily 50% capacity, but less capacity than the design conditions. So this shows how a variable volume system would respond under the same scenario as we turn compressors off. You can see point 4A now with 2 compressors running, or 3A with two compressors running. The suction temperature is still close to the design point, and VAV units for that reason are inherently going to take care of humidity better than a constant volume system will. So we've seen a lot of single zone VAV nowadays because of this.
So there's a lot of information on this, and to be honest, when one of our DX experts that we've worked with just retired recently, but he helped write the book on DX design. He did this engineering newsletter for the community, and I had to, read through this because some of it seems to be counterintuitive. When you look at like a chilled water coil or something that's very linear in the way it performs, in the way that the DX coils and condensing units work together can take some studying. So what we call this area here is the expected operating map of what should be considered. And the reason I jumped in here, Mike, is because I realized we have the Zoom chat feature, which some people have already done. And so instead of answering the questions we talked about earlier, Mike, if you want to pose them now and see if anybody can answer them in chat, that would be awesome.
So you see these blue lines have a start point and end point. Any idea what happens over there where it says compressor loading if you start trying to operate in that range over there?
No answers yet, huh?
Anyway, what happens is
What happens, Mike?
the last thing that the suction gas has to do as it leaves the evaporator, when it enters the compressor, it needs to cool off the motor. So there's each manufacturer limits the temperature that that gas can be to prevent from overheating the motor that's inside the compressor.
Mhm.
On the left side, we have the lines also end, and these are not actual compressor graphs, but they represent it. What happens on the left side if we get too far to the left?
In terms of operating points and saturated suction temperatures in this area. Does anyone have a good idea what happens? What can start to happen? No, Mike, you're gonna have to educate them again.
I think they're just shy today. Slugging. One panelist said slugging. Marty Williams. Actually, it's the frosting of the coil. If we get too close to 30 degrees, the refrigerant that is in the coil would make ice on the fins, and eventually you can actually freeze up the coil to where air won't flow through it anymore. So we want to, in HVAC, we typically try to avoid needing to have defrost on evaporators. It's heat pumps you can't avoid, that sort of thing, but with typical HVAC system. So there are additional controls. We have a thermostat that we call frost stat that we use to prevent that, or some people use hot gas bypass to make sure that the coil temperature stays above freezing.
Yeah, so just getting back to that and closing it off here a little bit, most of us don't even consider where our system might operate or go to this length as to what it might do at different variations of part load performance. But as we can see, this systems as a connected design system together will live here for 95% of the time, right? Our design conditions can be down to 0.4% ASHRAE. So it's really worthwhile exercise to do the cross plot, make sure that you're designing it as a connected system, and taking into consideration what happens in some of these part load cases, especially on a VAV. I did want to
Randy, if you would, Marty had an interesting point there we didn't talk about in this presentation.
Mhm.
Slugging. I'm not sure that everybody understands what that is, but why don't you go back to that basic refrigeration chart there, the third slide. I think it is.
Thank you, Marty. Always one for discussion.
What Marty mentioned slugging. What slugging is when where the letter B is, if any drops of liquid refrigerant make it that far, that's a real bad thing, because compressors are meant to handle gas, not liquid. So the purpose of the expansion device, there's two things that aren't shown on that, but the top thing up by in between the letter D and A, that's a bellows that in a mechanical expansion valve, it senses the temperature and the pressure over at point B. There's a thermal bulb that attaches at point B and a pressure tap that attaches at point B. And that tells the expansion device how much superheat, meaning how much you are above the saturated temperature. So it senses the pressure of the line, senses the temperature of the line. You want to make sure you've got 10 to 15 degrees of superheat in that gas so that there's no liquid making its way back to the compressor. So thanks, Marty, for adding that to your question there.
Yeah, I appreciate it. And then
we have another good question, Randy, by the way, in the chat right now in regards to the frosting condition. You mentioned the left side of the cross plot. The question is, aren't TXVs better than fixed orifice valves to prevent frosting under low load conditions?
Yeah, you're not going to see any orifice probably in this type of a system, but in small residential systems, that's the cheapest way to do it. But it's like the questioner says, it's not very accurate, but it all depends on the type of system. But in a commercial system, you'll always see some kind of an expansion device that is either a mechanical valve, or more recent systems have electronic valves.
A final clarification that I may have glossed over, but we refer a lot to the saturated suction temperature, the SST. A lot of us take it for granted, but most people coming in, no idea what I'm talking about. And when we talk about saturated suction temps is in the low pressure side here. Saturated meaning it's the temperature and pressure at which the refrigerant is going to boil off. And that refrigerant will evaporate at a constant temperature and pressure, but while still absorbing energy. So that's the temperature that we're targeting, and then anything above that. So after it's saturated completely as a gas, any temperature rise above that, superheat, and then as it's condensed at its saturated suction temperature to liquid, fully liquid form, any temperature decrease below that is a subcooling. So those are some of the terms that we're discussing here. Okay. So Mike, did you have anything else on the part load performance here?
I think we covered that pretty well.
Okay. All right, so now that we discussed some of the design fundamentals there, and if you have a nice balanced connected system ready to go on your design, as we discussed, is because it's a different world with the 410A and the microchannels and whatnot. It's when you go in and start looking at the details of line sizing and specialties, piping specialties, even down to the actual installation practices, are it's very important to refer and work with the manufacturer that you're picking to lay your design out on. Make sure that you're not just using the traditional rules of thumb or the some of the things we're used to. It's very important to work with the manufacturer and look at their literature and make sure that you're sizing and selecting things correctly for the system that you're laying out. Obviously, the more detail, the better. Mike's going to talk a little bit about some of the pros and cons of getting into more detail as a designer versus the installer. So we'll touch on that. But here's a great example here of a very diagrammatic split system, including specialties and equipment components. And so, as I mentioned before, 4 basic components: here, compressors, and TXV. But there's all sorts of things that go in between it. You have suction filters in order to make sure the refrigerant stays clean, shutoff valves, liquid filters, solenoid valves to avoid refrigerant migration during the off cycles. Moisture sight glasses, expansion valves are very important to select, to size properly, 1 per distributor on the evaporator coil. And even, different types of expansion valves. In some cases, you need a bleed port. Yeah, bleed port TXV valve that actually bleeds about 30% of the refrigerant, even in the off cycle. So keep an eye on that. As it comes to line sizing, I have an example here that counterintuitive to traditional line sizing methods. In this case, we have a set length and total elevation that we would allow the system to be installed, whether it's the condensing unit and the indoor unit are 5 feet from each other, or whether they're 100 feet from each other. No matter what, if they're within this realm of acceptable distance, there's only a single set of line lengths here that is needed for all of those cases in between. So, for example, here, if we had a 25-ton unit, on the suction line, you would want to put in for your horizontal and drops a 2 1/8 inch suction line. But note, in some cases, on the vertical riser, where again, as we talked about, it's important to ensure that the oil is entrained in the gas and returns to the compressor. In some cases, such as here, you would downsize that vertical suction line to 1 5/8 inches. Then with the liquid line, 7/8 across the board. So again, keep in mind some of the details there. So Mike, I'll turn it back over to you.
So now we'll look at some real world examples here. These are actual drawings that we've used on projects. So the one on the left here, this is the actual refrigeration piping plan that was on the drawings for that first 120-ton system I showed you. And you can see that it shows that 4 pipes are required, but it doesn't tell you what the size is. There's probably a note in the schedule that says that the contractor is supposed to size this per the manufacturer's recommendations. We feel it'd be helpful to have some, guidance as to what those sizes are for the manufacturer that you base the design on. The little drawing on the right here, that was something that, the contractor sent to us. We asked for a piping drawing. That's what they sent to us. The condensing unit was down here where the 11-foot leg is, and the air handler was up where the 3-foot leg is, if I remember right. And the guy went ahead and started piping, and it was contentious. We had to make some changes, and it just seems like we ought to take more care. Contractors spend a lot of time with coordination drawings on ductwork and plumbing and all sorts of things, but a lot of times they'll hand our submittal to a pipe fitter and say, put this in, and this is what we get. It seems like this piping is so important to the success of the project that we ought to spend more time designing it up front rather than just have the follow at the job site try to figure it out. So in contrast, on another project, I want to advance the slide. This is a drawing that we received from a contractor a few weeks ago on another project. And what it shows is this air handling unit number 1 was a 160-ton air rotation unit furnished by one manufacturer, hooked up to 2 80-ton condensing units on the left that are out of sight here, but the condensing units were another manufacturer, Trane in this case. And so this contractor called a conference call between the engineer, the 2 vendors, and himself, and had a lot of back and forth between everybody's requirements as to what was needed to do here. And afterward, he summarized it all in these drawings. And this was like a 7-page set of drawings that he was preparing for his field workers. And the Randy Circle thing, the only thing we found wrong with it was, well, there was some other things on other pages, but on this particular page, the suction lines were pitched the wrong direction. Trane now recommends that you pitch the pipes away from the compressor so that the oil doesn't come back in a big slug, because there's not that much oil in these compressors anymore. So that's really one of the few things we found. But the good news is that we found this on paper and not on a field inspection after it was all piped up. So what we'd suggest to the consulting engineers is to provide a layout of this quality on your drawing so the contractor has some idea of what he's going to be required to do. If he chooses a different manufacturer, it's up to him to find out what that manufacturer's recommendations are. And so a note in the schedule would be contractor to submit a piping drawing for approval prior to installation. So we think this would go a long way to make these jobs go smoother.
Yeah, thank you, Mike.
So if you want to go to the next slide here.
Yeah, I'll go next slide here. Any questions, or we'll keep going? Okay. And then obviously just to touch on Mike's thing here too, this is an extremely detailed version of, right? We showed you the 2 extremes, so somewhere in between is probably feasible. But so as we transition out of it sort of completes the DX design discussion in detail. We think it's a good time, or we'd like to remind people, and we've learned too, that it's sometimes worth taking a quick step back after the application's done, or you're about to decide which type of system you're going to go with, and DX was your original choice. just to check. So certain applications, like very critical applications, healthcare, tight discharge air temperature control, tight humidity control requirements. A lot of these things can sometimes are maybe not the right application for DX. So it's always worth looking at why did you go DX originally, and maybe worth a final comparison, because when you compare some of the newer systems of packaged chilled water plants that are available now from all different kinds of, even with pump packages, all that, it starts to almost look very similar to if you purchased a DX split system, with condensing unit and indoor coil. So it's good to weigh the pros and cons, especially with the new technology of both types of systems, and really make sure that you're picking the right system for the application that you're looking to do it. I know that I've spoken with a number of engineers recently over the past 2 or 3 years that they've been forced to actually look at some of their design specs and standards when it comes to DX. Where it used to be a default, we're going to put DX on there. They've had a number of problem jobs that they've had to go back and analyze and say, well, might have better use a chilled water system there or something. So just a little plug there that we want to make sure to keep in mind during the early design stages. Mike, anything to follow up on that?
Yeah, well, that thing, total cost at the bottom, we did look at a project just recently that we'd sold that we repriced it with chillers. So the original system had 2 rooftop air handlers were sitting right next to each other. With one had 100-ton condensing in it, the other one had a 60-ton condensing in it. So we repriced it with 2 air-cooled chillers and some pumps, and surprisingly wasn't that drastic of a difference. The contractor said the piping might be about a wash with all the complications of the refrigeration piping versus just a simple chilled water loop. So it wasn't an order of magnitude difference by any stretch of the imagination. So it's worth taking a look at. And in the next slide, I'd like to show you one of the benefits that we see to a chilled water system. This is actually the air handler in our office. I had somebody take a screenshot yesterday as to what it was doing about noon yesterday. If you remember, it was kind of a chilly day. Shows the air temperature was 65 degrees and the unit was an economizer. Now this is a 16,000 CFM air handler that serves an 18,000 square foot office. Did I say CFM air handler? So it's a 16,000 CFM air handler serving an 18,000 square foot office. And we have an ice storage system in our building that makes real cold water. So this is designed to provide 50-degree air to fan-powered boxes. So the airflow is maybe lower than you might see in some systems. But the point is that it's 65 degrees outside. The fan would heat that air up to about 67, and it wouldn't be adequate to cool the building. So what we had going on yesterday, looks like we had 3,300 CFM being delivered to the boxes, and the coil was cooling the air down to 50 degrees, which was the design. And it was probably doing it just strictly off the ice. The compressors probably weren't even running at that point. So this shows you the things that you can do. If this was an air-cooled condensing unit, this would be like the worst day possible for a DX system because the load is low. As we talked about, the condensing unit actually has more capacity on a 65-degree day than it does on a 95-degree day. So it's going to be struggling to try to maintain that 50-degree leaving air temperature for us.
Yeah, so as we talked about, we're asking these really large DX systems to do a lot on the really big applications when we're applying things like VAV airflow control, part load, economizer. If you compare that against something like this that is chilled water valve, simply modulates 61% at a constant temperature, 39% VAV, just inherently can handle it maybe a little better in some applications, right? So it's something we wanted to bring awareness to. So at this point in the presentation, we may somewhat drastically switch topics here to more along the lines of the VRF split system. Before we go, is there any final discussion points that anybody want to bring up regarding the past DX split systems, because as we jump into VRF, I think it's going to change it up for all of us. Last chance. Except for at the end when we ask a Q&A. All right. Thank you, Mike. So the other portion that we're bringing up during this presentation is new quote technology, which is pairing the VRF systems with third-party air handler or evaporator coils in general in that application. So it parallels a lot with our DX discussion in the sense that they're the same type of generic design where you have an outdoor condensing unit with the same components out there, and then you pair that with an indoor unit that also contains evaporator coil and expansion valve. So it's the same idea, and some of the benefits that are, I'll follow up on the benefits after this, but for now I just want to do a little overview of how that compares with the traditional DX systems. So if you look here, if this is our outdoor unit and it's connected with refrigeration, similar suction and liquid lines, we can call them that, but there are all sorts of mixed phases in a VRF operation. Those are paired with an evaporator coil that is not manufactured by the VRF, which, you know, most often in VRF systems, any indoor unit, whether it be a high wall, cassette, whatever it is manufactured, designed, tested, pre-tested with the outdoor unit ahead of time. So it comes as sort of a package. I think we're all familiar with that by now. So this is a unique application because VRF systems themselves are designed around such tight tolerances that trying to inject and have the system operate with a totally separate third-party coil can produce some challenges. So the most basic function of this as a heat pump coil is, again, we have a suction low pressure line coming out of the coil here, and then a liquid high pressure line coming into a distributor. Instead of having a thermal mechanical expansion valve with the bulb that's measuring the suction line temperature, like Mike described earlier, which is mechanical, they actually replace it with an electronic modulating expansion valves. Sometimes they'll call it just electronic EEV valves or linear expansion valves, something that's actually controlled and modulated with like a stepper motor usually. So that allows it to work with the actual variable flow of refrigerant through the coil. Now, the other difference is that you're actually measuring the temperature and inherently the pressure, since it's linear relationship in a refrigerant, of the inlet and outlet of the DX coil. So you're not just monitoring the suction temperature and modulating your valve like traditional systems. You're actually measuring the differential, or the VRF system that it's connected to is measuring the differential temperature at all times. And then it's literally kind of guessing on what capacity that it's delivering to the airstream or absorbing heat, whether it's in cooling or heating mode. So that is the main difference and why it's a lot more complicated than our standard traditional DX systems, because it relies a lot on the coil design parameters and the physical limitations, or the physical parameters, min and max volumes and coil size, because it needs to know all that so that it has a good idea of what capacity it's delivering as it's modulating its electronic expansion valve. So, final note on the quick overview, which again, it could be a whole presentation, but that's why it's extremely important to review your design and install details with whoever you're working with on the VRF side for the manufacturer. Make sure to run it through the selection program and go through the design in detail. And then to discuss some of the benefits of moving to a VRF type of split system instead of the traditional is, many times we've even been forced into the VRF system strictly on the extended line length and elevation limitations, where traditional systems might be limited by 50 feet or elevation and total of 150 feet split max. Some of the new VRF systems can go up to 350 total feet in high rises downtown Chicago market and all that. It can be quite beneficial for these types of systems to be paired with just a regular air handler. You can do space temp or I'll just be honest, a little crude version of the discharge air control. And then the cooling and heating operation is a plus, since it's a single coil that can provide heating as well. And then inherently the increased energy efficiency that we're all familiar with in VRF. So there's some of the benefits of why we might choose VRF over traditional DRX. And my final slide, it's a little wordy here, but one thing, like I was discussing a little bit earlier, and as technology advances, some of the limitations are getting in the barriers as to why we're not using VRF for everything. Right? Some of those are going away, but as you start to lay out this design, it's really recommended that you just be aware of the limitations of the VRF system compared to our traditional systems. And I think that's the biggest issue that I've seen in the past. It's not that we go into it, thinking it's going to do everything it does. It's just, it's different than what we're used to. So some of the things, like the biggest one, for example, is the complex air handler sequences. The VRF system is separate and meant to be maintained and does its own thing. And then we, and the BAS sequences that we're used to, want it to do this stuff over here. And a lot of times they don't mesh well. So it's something that needs to be looked at. The earlier, the better in advance, just to avoid surprises further down the road. Another big one for Chicago, just keep in mind, is the minimum and maximum required entering air temps. Now, these aren't just kind of like the mins that we might tell you on a heat pump that, if you're giving it less than 35 degrees airs or 35 degree entering air, it might freeze up. This is more like the VRF system is literally measuring the entering air going to the coil, and it's hard coded so that if it's below or above a certain temperature, it might not even let it cool or heat. So, there's some of the details just to keep in mind when you're doing it. In Chicago market, always recommending 100% backup heat in critical applications where you might be trying to use it for DOAS or even just really tight temperature control. These things are actually, I've seen them extremely successful in cooling only applications where you already have your heat figured out, with whether it be hot water, electric, gas. And if you're just using it for cooling only, the VRF systems paired with a third-party coil here actually do pretty well. So, and then on the DOAS, or if we look at the discharge air temp fluctuations, keep in mind when you're applying this to, let's say something like a data center or it's even healthcare. A lot of times the discharge air temp, this, plus or minus 2 degrees, 3 degrees, people actually might start noticing that. So VRF, probably not the best application for something that needs to have that level of control. Finally, another big one too is for the VAV capability of it. We do recommend, for really reliable performance, no less than about 60% airflow turn down. There's cases where it will work better with more turn down, but from experience so far with the current technology, that's kind of where you'll be safer. And constant volume obviously is going to be a better bet if you can do it. And then other than that, the final note when looking at VRF applications is to consider the different modes of operation that, again, we're not used to with traditional DX split systems or chilled water or anything, right? There's periodic, call them smart modes, that are built in, such as defrost mode, where inherently it's a heat pump, right? So in our cold Chicago winters, it's going to have to defrost that outdoor coil every so often. There's going to be some sort of hit in performance as it goes, even if it's multiple VRF systems that may be staging to overcome when one is on defrost or not. But still, there's going to be a hit on performance. It's not going to be constant. So just be prepared, and hopefully the application allows for these variations. So other than that, we're right on time here. So that is it for our presentation so far. Until we move into any leftover Q&As.
Yeah, we have a question here. Is the 60% turn down limited to mainly VRF systems, or does it also apply to typical DX air handlers or rooftop units?
So that is strictly on VRF systems for this presentation. And then, Mike, what do you see on the turn down for split systems normally? Limitation?
Yeah, we wouldn't have that same limitation. I think that they can certainly go down to 30 or 40% most likely.
Yeah, and same with RTUs, especially like packaged rooftop units. You know, they're all designed to the DOE, Department of Energy minimum energy efficiencies and capabilities now, especially along the lines of IECC, or 90.1, sorry. So all of that requires like single zone VAV operations and true VAV operations, at least down to 33% minimum airflow.
It also kind of depends where you're starting too, that the, if you're starting off at 400 CFM per ton, that's a lot different than if you're starting off at 250 or something like that. So some of these systems are pretty low when they start.
Mm-hmm.
We have another question here. What are the proposed refrigerants for DX split systems, since R410A usage will be going down over the next decade?
We've only heard of some science projects so far. Nothing in the tight plans that I'm aware of any recently. As to rooftop units and package style DX systems, right? That's not in the focus of the people making legislation right now. And I don't know, Mitch, or do you guys, I forgot the name of that one that they're testing somewhere in California. I think there's a few up in the air right now that they're not sure, but there's not a lot of pressure right now from regulation side of things as to what's going to go in replacement for those. So I think they're still experimenting is the good answer for that one. And there's no clear winner yet.
Do we have any final last questions? Anyone that's on? Looks like VRF has freon unoccupied spaces in case of fire, pipe joint melts, and freon enters room and burns. Is this considered?
You say that again, Mitch?
VRF having refrigerant in the occupied spaces is cases of fire, pipe joint melts, and freon enters the room and has a flammability issue. Is this considered in design right now?
Yes, that is actually a big portion of design considerations, and we really recommend along the lines of ASHRAE 15 and inherently ASHRAE 34, which defines the refrigerant. ASHRAE 15 defines the mechanical room requirements for dilution volume, so maximum amount of refrigerant parts per 1,000 square feet or cubic feet that is allowed. And the way that you do that, because you have to treat a VRF system as whichever room, the smallest room that it passes through, we have to treat it as all of the refrigerant in that VRF system could potentially be released into that smallest room. You'd have to do a calculation to see what your maximum concentration is in the smallest room. And then with the VRF system itself, if it's over that, there's techniques you can do to break it up, make the volume smaller, maybe make one bigger system, two smaller systems, make the room larger, duct into the room. It's definitely a consideration you want to keep high in mind. And if you comply with ASHRAE 15 as worst case, all of the refrigerant dumps in that room, you're below the dilution level, then you are per code and acceptable to design it that way. Now there's further mitigation techniques you could do, such as direct room sensors for refrigerant monitor sensors that would alert the VAS system. So there's a lot of technology coming out that can go a step further in actually detecting it at the room level.
Another couple questions here. The first one would be, can you provide some guidance for distances, both vertical and horizontal, between air handlers and condensing units to make sure oil return to compressors is not compromised?
Yeah, so we have a piping guide that we can send you if you email one of us here. We cover Trane equipment, but like I said, you need to contact the manufacturer that you're dealing with. Our guidelines are strictly for Trane equipment.
Yeah.
And we have another question here. How does low ambient cooling affect refrigeration piping in both commercial split systems as well as variable refrigerant volume type split systems?
Okay, well, low ambient is usually an accessory. We use several different methods, either variable speed fans on some products or damper on the fan for other products, but basically what it does is elevates the condensing temperature on cold days by reducing the airflow across the condenser coil. So that typically would take you down to 0 degrees ambient Fahrenheit. There are other methods that can be employed to get you below that, but they get to be pretty complicated. So go ahead.
So in strict terms of refrigeration piping, if you look at the question, right, then there would be really no difference in your actual refrigeration piping in a standard application versus low ambient application, right?
Could you touch on flooding the condenser for low ambient conditions, for ultra low ambient?
Okay, so that's a technique where the surface of the condenser coil is reduced by flooding the condenser coil with refrigerant, if that makes sense. You figure that most condensers have 3/8 inch tubes in them, so they hold a certain volume of refrigerant. The surface area of that refrigerant, if you fill the tube halfway full of liquid, you've reduced the actual heat transfer area that's left. What's involved, a lot of data centers use this on computer room units where you'd have another device right where it says liquid line. You'd have a tank of refrigerant there, a receiver full of liquid. And there'd be another valve that would go from where the discharge line is, that you'd have a valve over there that would send hot gas from the compressor discharge over to that receiver, and it would pressurize that receiver with hot gas to force liquid down to the expansion device. So as it did that, as it displaces liquid from the receiver, flow has been cut off then from the condenser outlet, and refrigerant backs up into the condenser to limit how much surface area is available for condensing. So this is a very common way. It'll typically take you down to -20 Fahrenheit. And most computer room systems use this for data centers.
They use that in commercial refrigeration too frequently, right, Mike?
Yeah.
Okay.
Liquid to flow through that expansion device, there needs to be a pressure differential between D and A. If the pressure in D is the same as A, nothing's going to flow anywhere. So we need to boost the pressure in that liquid line enough to force liquid through from D to A.
Yeah, I should have included the classic pH diagram, but it's me to fall asleep.
I'll get another question here. We normally do not see hot gas reheat options in split systems as we see them in packaged DOAS units. Why is that?
Well, it's hard enough to design a piping system with just these two pipes, and it all gets down to refrigerant management and oil management, and I'm not saying it can't be done. It's just very difficult to try to put something like that on a drawing where, you know, the ones we do in the factory, and we've done hundreds of them and we know how it works, but they've tested that in a laboratory setting and they know what the limitations are.
Yeah, one of the biggest challenges too in the split system is, you know, when we've gone to microchannel coil and reducing the volume of refrigerant, when you add another coil into the mix, such as a hot gas reheat coil, it's very difficult to ensure that the refrigerant is balanced as it travels from either the condenser or the hot gas reheat coil, because a lot of times it's, you know, it might be modulating hot gas reheat is what most market is requiring right now. So in order to keep the refrigerant balanced and not starving either the compressor or the condenser, and like Mike said, ensuring that oil travels throughout all parts of the system is not getting trapped in spots here. Once you try to do that in a split system where you leave all of the in-between piping, you know, you need 3 pipes at that point, up to the field, there's a lot more risks there in compressor burnouts, oil management. And so even when it is offered and carefully designed with the manufacturer you're working with, you still want to, still a lot of times the length limitations are like cut in half. If you might have been allowed 100 feet before total separation, now they'll say maybe max, you know, 50 feet or something. And even then they want to be in charge of strict pipe sizing guidelines and all that. So
You see it on computer room units again, where the compressor is typically in the indoor unit instead of out on the roof. So now they've got a little closer control on the piping from the discharge of the compressor to the reheat coil and back to the evaporator. They can control that a lot better. But when your compressor is far away from the system, it's, you know, if you think about the hot gas that you're sending to the reheat coil, is probably going to condense a bit on its way to the reheat coil if it's far away. So it's not saying it can't be done. It's not often done.
Any other final questions?
well, thank you. I know we went over a little bit here, 8 minutes or so. So we appreciate everyone's patience this evening and thank you for joining us.
And we'll be sending out a survey regarding the presentation coming directly to your inboxes from ASHRAE. If you please take some time to fill that out. I know everyone would appreciate the feedback. With that, I hope everyone has a wonderful evening and thank you everyone for the time.
Thank you.
Thanks, guys.